Good evening. First of all, I would like to thank you and Lee for this very kind invitation and introduction for my talk. And I choose today to talk about some project of research that we have undertaken around 10 years ago now, and in collaboration with Nikki. It was about mental time travel and what we have done in cephalopod molluscs, so mainly in codfish, but I will talk to you a bit of octopuses if I have time. So as you all know, episodic cognition ability making us able to travel backward and forward in time, to make us able to re-experience past events and so to imagine possible future ones. And what we know from literature is that past and future mental time travel share a lot of common features, physiological features and developmental and other neurological features. For example, some few examples, we know that both in mammals and birds and many corvids, when in a species you have been shown episodic memory, we have also future planning. Another common point is that both these abilities are known to develop very late along development, and they are very sensitive to the effect of aging. And lastly, what we know also is that there is an overlap on the neural regions that are involved during aberration, can be when we try to remind something that happened to us in the past, or when we try to imagine something in the future. So all these common points have made people try to understand why they are here. And one possibility is that some say that it's the same cognitive abilities, but there are some other possibilities. And for example, it could be two different cognitive abilities that which have a close intertwined evolution, one being the byproduct of the other. For example, some authors like Klein say that episodic memory has evolved to allow future elaboration. So episodic memory serves like a database with all the features of the past events that we've been through, and we can use them to reassemble them flexibly to make some different future potential scenarios. The other possibility is that they have separate evolutionary histories. But in this case, all the common points that we see could be linked to the fact that they are subserved at the same simulating system. And that's the point that we have here, is that mostly people have been working on this species, so primates, rodents, corvids, to try to better understand episodic cognition, but they have maybe a common ancestor that has been at the origin of the evolution of this complex cognition. And it could be very important to have something that a more inclusive and comparative framework to try to better understand the evolution of mental time travel. Animals that have a completely different evolutionary history. That's why we can wonder whether we can study cephalopod mollusks. First reason is that we know that their cognitive abilities have arisen completely independently from the vertebrate lineage. We consider it 550 million years ago. Second reason, they have a very complex central nervous system, centralized, highly organized, and we know that they are known for their very flexible behavior. So among the cephalopods, because I don't know if everybody knows quite well cephalopod mollusks, we have two main groups of living cephalopods. So we have the shell cephalopods here that you can see, the nautiloids, who have an outer shell, and you have the modern cephalopods, so the coleoids, mainly the octopods, the cowfishes, sensulato, and the squids. So what am I going to talk to you today? There will be three parts. The first part of my talk will be quite longer, is this one. We have shown at first that codfish have possessed some kind of episodic memory abilities. I will talk about the procedure just after. But the first thing is, we know that some features are indicative of episodic memory because they can remember what happened, where and when, and this from unique past events. But there are a lot of other features that can be interesting to explore, whether it brings some flexibility in their behavior, whether they're able to retrieve the source of their memory, for example. So we'll focus on that. The second part, we try to understand, and we are trying to test whether the fact that cuttlefish possess episodic-like memory is negative of the existence of future planning abilities. It would be the case if episodic memory has evolved to allow future planning. So we wanted to test this, the fact that it's concomitantly found in the same species or not. And quickly, we'll focus on another species. So Octopus vulgaris, we have done some experiments on this species just to know whether what we have found and described in cuttlefish is something that is very specific of this species, because it could have evolved to match the cognitive capacity to certain ecological demands that are very species specific. And that is possible because even if they resemble each other and they have almost the same brain, what we see is that they are exposed to very different pressures. They are not eating the same type of prey. They have different way to interact with other individuals of the same species, and this could have led to different pressures leading to the selection of their cognitive abilities. So let's start with the first part on behavioral features that could be indicative of retrospective mental time travel abilities. So why cuttlefish? Because I was working in cuttlefish since years. I've done my PhD in cuttlefish on spatial navigation, spatial memory. But cuttlefish was not just choosing like this. It was not just an opportunity. It's very specific. We know from a paper published in the lab that they have very strong food preferences. For example, they can eat fish, crabs, shrimps, but we know that most individuals prefer shrimps over crabs, for example. And what is also very particular is that it has been shown in another species that they spend 90% of their day resting. That means that 90% of the 24 hours, they are just not moving because they are just lying on the sand, because they are buried inside the substrate, or maybe they are eaten in crevices. So they don't move most of the day. The thing is that when they hatch, they are more or less 1 centimeter long, and 2 years after they can be big like this. That means that when they go out to forage, they really need to know where to go and when to go to be very efficient and to be exposed a minimum amount of time to predators. And so that was, for us, a very huge ecological pressure that could have led to the emergence of this ability to know what happened where and when. So do they remember what they've eaten, where and how long time ago? First of all, we have to make cuttlefish answer our question, and we are, for most of the experiments that I will show you today, we are using some kind of visual cues, and we teach them to go to visual cues, touch it, or just sit in front of it to make a choice. So when they are pre-trained to show a choice, we can start the experiment. This experiment is really what has been done in chase, but at the reversal. We are not interested in food degrading over time, but on food replenishing over time. And that's very important. So as if you are familiar with other experiments run with COVID, we have different trials, and each trial is constituted of 2 steps. For the first step, we place 2 visual cues, exactly the same, in the tank of the cuttlefish. Cuttlefish has been trained to go next to a visual cue to go for food, but here they go randomly next to one of the cue. When they go next to one of the cue, the 2 appropriate prey are provided, one at each location, and the cuttlefish is allowed to eat their preferred prey. So here we can see that the cuttlefish went to the visual cue on the left, but saw the shrimp on the right, and finally went to catch the shrimp on the right. So that was the first step of a trial. The second step occurred randomly, either after a short time interval, so 1 hour, or a long time interval, 3 hours. So it was randomly decided. And what we were expecting is that when they are tested after a short time interval, we were expecting cuttlefish to go where they have seen their non-preferred prey, because they ate their preferred prey 1 hour before and the time was not enough to let the food replenish. But when they were tested after a long time interval, we expected cuttlefish to go back to the location where they have seen their preferred prey. Time is enough to make food replenish. So even if in the second case, going here, make cuttlefish get a crab, and going here, make cuttlefish get a shrimp, this would be considered as an optimal choice according to their food preferences. So we made this experiment, and of course, to make each event unique, the location of the two visual cues were changing every day. Of course, they were the same place for the first step and the second step of a trial, but from one day to another, everything was changed. So every day, cuttlefish needed to learn what is where and keep track of time to know whether time elapsed was more 1 hour or 3 hours. So here are the results that we found for 3 individuals. The percentage of choices for A6, B6, and B13. And what we can see is that when they are tested after 1 hour, cuttlefish are mainly going to the location where they have seen their non-preferred prey, the crab. But when they were tested after a long time interval, they are mainly going to the location where they saw their preferred prey before. So to have this behavior changing, they must have learned what they have eaten when, how long time ago. So that was the first experiment we made together, and which showed that they are able to match their foraging behavior to the replenishing rates of different food items. So this what when were memory of unique events. So that was the start. After that, the question we get is that, okay, we know that this kind of memory, episodic memory, is known to be very sensitive to the effect of aging. But for cuttlefish, we have no hippocampus. So we can ask ourselves, would I have exactly the same decay of memory along life or not? So we wanted to see if there is an impairment of spatial-temporal learning abilities during aging. But what we know from humans is that it's specific to the episodic memory and not semantic memory. It's not just because there's a spatial component and a temporal component, it's because it's something that is more linked to another kind of memory. That's why we wanted to see if these two kinds of memories were altered or not during aging. And the time course was different. So this is another procedure that we designed. In this case, this is more a rule. There's a spatial temporal learning, that's a rule. 3 visual cues inside the tank, but always at the same place every day. But when cuttlefish are tested at 9 a.m. in the morning, if they go to this place, they get some food. When it's at noon, they should go to this place. And when it's at 3 p.m., they need to go to this place. So cuttlefish need to learn when it's in the morning, I go there. When it's at noon, I go there. When it's in the afternoon, I go there. But this is a rule. They don't need to remind what happened just before to answer the question, because it's something, a rule that is the same every day. And what we saw here is the mean percentage of correct choices among our individuals. In light gray, we have the subadults. I forgot to tell you who are the subadults. It's the 1-year-old cuttlefish. Cuttlefish live 2 years, at least the species we are studying. They live 2 years, and so this is 1-year-old cuttlefish, just middle-aged cuttlefish. And what we can see is that, of course, the first day adults, 2 years old and 1-year-old cuttlefish, are around 33% of correct choices, because they have 1 chance out of 3 to find by mistake, by random, the correct choice. And we see that we have an improvement of the ability to answer, and we see also that there is no difference between 1-year-old cuttlefish and 2-year-old cuttlefish. Okay, so now if we go to another kind of memory, so this episodic-like memory, do we have the same profile? So this is exactly the same test that I've explained you before, but except that rather than using crabs, it was frozen prawns that were used as non-preferred prey. And here is the number of trials to reach criterion, because cuttlefish were trained with 1 trial per day, randomly after short or long delay, and they were trained until they reached a criterion of 9 correct trials out of 10 consecutive ones. And what we see is that there is not very huge difference, because there are 15 and 10 around. So that means that cuttlefish are doing the proper and appropriate behavior as soon as they are tested. So there are no difference between old cuttlefish, very old cuttlefish, and middle-aged cuttlefish. That's not so surprising for 2 reasons, because what is known from some studies that dates from the 80s, from the Raymond Chiche-Rislam, what he saw is that when you look at the brain and during aging, you can start seeing some degenerating fibers inside the very highly associative centers only when they stop eating. And usually when they stop eating, it's 3 days before dying, 3-4 days before dying. But before they stop eating, you can't see in this part of the brain any alteration. And the second reason that was not so surprising is that cuttlefish reproduce once in their life at 2 years old. So it's very important for them to be able to keep their memory abilities intact until the end of the race. It's like trying to get big as fast as possible until 2 years to reproduce and die thereafter. So for all these reasons, it's not very surprising from an adaptive point of view and for biological point of view. What we know is that events are not encoded like a film strip that would be encoded somewhere in the brain, but it's more like we are learning all the features that were present where we live an event, and we are splitting them and storing them. And when we want to recollect an event, we are trying to catch some of these features to reassemble them and to recreate a souvenir. So that's the way. And the idea of that is that we can, according to the source memory monitoring framework, we have this way to check that everything is well reassembled together, and source memory helps us to find the origin of the souvenir by retrieving specific features of one souvenir, not to be the same, that's a very similar one. So we wanted to know whether cuttlefish were able to retrieve some features of their past memories. And the question we wanted to ask them was, have you seen or smelled something before? But using the unexpected question paradigm. For this, we needed to make cuttlefish answer our question. So this part is not the source discrimination task, but just training that was useful for the rest of the experiment. And here we place a glass tube inside their tank. And so if they see something in the glass tube, they should choose a cross. When they smell something in particular in their tank, they choose the arrow. And when they don't smell something, they choose the black square. So 3 items were chosen for training, so fish, crabs, and shrimps. So either placed in the glass tube or either the other or in the tank. It was important to have this control part because if not, cuttlefish could have learned there is something in the tube or there is nothing in the tube. That was the way to make sure that they learn that it is smelling versus seeing versus smelling. Of course, we needed to check first that they understood the rule. So for that, we make a transfer test by using an item not used during training. So for example, here muscle. So depending on individuals, what the order of or the actual muscle inside the glass tube. And of course, if the cuttlefish choose correctly the pattern, that means that they understood the rule I see versus I smell. When this is okay, we can do the source discrimination task. In this case, we have 2 steps. We are placing in the tank either something inside the glass tube or in order inside without anything in the glass tube, using another item. But in this case, contrary to what happened during training, they were not allowed to make any choice. No possibility to say, oh, I see or I smell. Because here it was made in parallel. They were exposed to that and they're choosing at the same time. Here, no possibility to choose. So after 5 minutes, everything was taken away and the experimenter leave and the experimenter come back 3 hours later. And 3 hours later, the experimenter asked, have you seen or have you smelled something 3 hours ago? And to make cuttlefish understand that the question was not about what is happening currently, but before the white square was taken off. Like this, cuttlefish wouldn't have the possibility to choose, I see nothing, I smell nothing. But this is the unexpected question to make them retrieve in the past information that has been stored unexpectedly. So yeah, cuttlefish are very good at this kind of task. So the cuttlefish succeeded the transfer test, whatever they were tested either with the order of the new item in the tube, and for the source discrimination task, they were very good also to do that. Of course, when we see that, we see, okay, there's 100%, okay, they're very good at that. But what was more interesting, but we have not quantified this very precisely, is we can see the decision making by the cuttlefish. We're talking before with students, saying that sometimes you can see by changing the color and the behavior that they're hesitating. And typically when we're doing this kind of question, very unexpected, we can see a difference in the behavior they have compared to what happened before. You can see the cuttlefish are starting to put the head out of the water, look at the experimenter, looking at the visual cues, then again, what happened? What do you want? Okay, and after they choose. So there is a process of decision making that is very very accurate, and you can see very well. So what we see here is that after being unexpectedly asked, cuttlefish are able to retrieve whether they smelled or whether they saw something 3 years ago. I'm not saying that we have shown source memory here in cuttlefish, but at least we show that are able to go back to retrieve one of the features of an event from the past, because they didn't mean that they would need that in the future. Okay, so indirect way to explore source memory is just to try to see what happened when there are some errors, and errors occurs, of course. And if you have errors occurring, that means that you have this constructive process ongoing. So we wanted to use a paradigm with 2 different events, sharing a lot of features, sharing a lot of features to know whether at one point a feature of one event go to the other event when they reassemble the event. So first, the control. Here we place 3 glass tubes with a pattern. There will be a small video just after. So 3 glass tubes, different patterns, and they can see what's inside. So in this one, they can see their preferred prey, so shrimp. Here it's empty, and here their non-preferred prey, the crab. After that, there is a second event. The tubes are rotated, like this, they can't see what's inside, and we just show them the tube that was previously containing shrimp. And of course, after a 1 hour delay, if we ask them to shoot in these 2 tubes, this one was previously empty, this one was previously with their non-preferred prey. Of course, it's better to have a crab than nothing, though we're expecting cuttlefish to choose this one. And of course, it's what they do. So here we place the 2 tubes. So the one on top was previously empty, the one on the back was with the crab, and we can see cuttlefish coming slowly, choosing, coming back. Very delicate animals. So that means that they are able to do that. They are able with 2 events to choose after accurately, and there is no problem for that. But we made also our false memory test by adding what we call a misleading event. In this case, during this misleading event, we place the tube previously containing shrimp along to the tube previously empty. The idea is trying to make them think that they have seen a shrimp inside because they've seen this tube twice next to this one. And what we found, indeed, that we have misled the cuttlefish. When we are doing that, we have no preference. Half of the cuttlefish are choosing the tube that was supposed to be previously empty, and we know that they're able to remember that. And here they're choosing half of this one, the cuttlefish are choosing this previously empty, and that's nonsense. And this is half of the cuttlefish choosing this one who previously had the crab, so the good answer. And the explanation of that is that it could be like, as we have in a lot of studies, three kind of individuals. Some individuals are not sensitive to the formation of false memory, so maybe they can choose this tube that become a problem. Some individuals are very sensitive to the formation of false memories, and in this case, maybe they will think and choose this one as, okay, I've seen shrimps inside. And you have also one part of the individuals that are completely misled, and at the end, they don't remember anything, and they are just choosing randomly one of the two tubes. That's why we could have this 50% choice of one and the other. So it would be interesting to go further in this experiment. There are other controls, but not possible to show you everything, but that was the main result to have. Okay. So if we go to this retrospective part of mental time travel, by trying to test different features, we saw that cuttlefish are able to retrieve some features of a previous event, not only what were when, but also the perceptive features, what I saw, what I smelled. And it's maybe a way to get closer to the phenomenological aspects side of episodic memory, because cuttlefish have to know consciousness of their own modality, sensory modality that have been involved during these events. And using this unexpected question, it was very important to have this test because in this case, animals need really to retrieve something from past information, because when we look at the episodic memory task, of course, it's the same rule. So maybe cuttlefish can learn for later use and information. Here it was not the case. When we can go next to the other part of mental time travel, so more future-oriented ones. And I will start with that. We know that from the literature, some people will say, oh, cuttlefish are very opportunistic foragers. And you have papers saying, no, cuttlefish are very selective foragers. Nobody is very happy and everybody has his own way to understand things. And we try to think whether it can change. So we had here two groups of cuttlefish. This one had during daytime, every day their non-preferred prey, crab, they can eat or not, whatever they want. And during nighttime, every night they had access to their preferred prey. So it was really predictable. In the second group, they have also access to crab during the day, but during nighttime, it was not possible to predict the presence of shrimp because they were randomly nights were randomly assigned to shrimps or no shrimps. And to what we saw here is that here's the number of crab eaten during the day. Here it's predictable. Here, when the presence of shrimps, the preferred prey, will be available at night, we see that cuttlefish start lowering the consumption of crab during the day. One block is 4 days. So they are lowering the consumption of crab during the day. They are more selective. When the presence of shrimps during night is not predictable, we see that they maintain their consumption of crabs during the day. And what we show also is after 8 days, we reverse the conditions and we see exactly a switch going very fast. So they can switch very efficiently from a selective to an opportunistic strategy, and this very quickly in only a few days. So we wanted to go further and to test whether cuttlefish are able to exhibit day-to-day flexible foraging in response to the rules that acquired from their past, and depending on what they know that will happen in the future. So in this case, they had access to crabs every day, but cuttlefish had access to their preferred prey, shrimps, one night out of 2 on a regular basis. So it was really predictable. Shrimps one day, the other day, no shrimps, etc. And in this case, what we can see in this case is that they are changing their foraging behavior. Here in light gray, what we can see is the consumption of crab when they know that shrimps will be available at night. They are restraining themselves to eat the crabs during the day when they know that the preferred prey will be at the dinner at night, because if they are eating too much, they won't be hungry enough to eat their preferred prey. But here, when they know that they won't have any shrimps for dinner, we see that they can keep consuming the crabs during the day. So that means that they are able to take a decision depending on what is going to happen in the near future and depending on what they have learned from their past experience. So that was a very important result. So we saw here that their predatory behavior, that most of people, when you read all papers, say that's very stereotypic behavior, we see that this can be adjusted day by day and going from selective to opportunistic behavior depending on environmental conditions and predictability of the environment. But they are also able to flexibly choose each time what to do or not what to do, depending on what will happen in the future. So this is a future-dependent behavior. The question was, and we've been talking about that, can we call that future planning because they are doing something for later? And say, no, that's not enough, okay? It's future-oriented for sure, but to be sure that it's future planning, we have to be sure that the decision taken in the present is taken according to their future need, independently of their present need. But during the day, the present need is maybe, I would like so much to have some shrimps now. So that was not control. But we are not able to talk about future planning here, but at least it's future dependent. So we wanted to design a proper experimentation to explore future planning in cuttlefish. What we've done, it's in several steps. So here, in the separators, we have a cuttlefish and we give them shrimp. They put a shrimp, they eat the shrimp. We put another one, another one, another one, until they stop eating. They are really fed to satiety. And when they are fed to satiety, we let them, after the access to the wall apparatus, they have the choice here to go inside an arm where food is available, or they can go to the arm of the maze where a shelter is available. What happened here, of course, they have been fed to satiety. If you ask them, do you want to eat or do you want to hide, they will go to hide. So the expected choice was, I will answer my current need to hide because I'm not hungry. During the night, what we done is we locked the cuttlefish in the arm chosen, like this, without food during the whole night. And the day 2 was really a test phase to see whether they could prioritize their future need to eat rather than current need to hide. So the process was exactly the same. Cuttlefish were fed to satiety here until they don't want to eat shrimp anymore. And after they're given a choice between the arm with a shrimp, or with shrimps at least, and an arm with a shelter. And if they are planning for the future, we're expecting cuttlefish to go to the arm with a shrimp. Why? Because later they will be happy to eat some shrimps at night because they won't have access to food, and because this is at the end of the day, so lights are going to be turned off in a after a very short time interval. So that was what we were expecting. Just showing video. So cuttlefish coming out, choosing food, going food, shelter. Shelter is better. So in this experiment, we also make different groups by changing the value of the shelter to make it much more attractive to have a maze lighter, to have sand, to make more attractive or less attractive to change. But what we found is whatever the test, whatever the cuttlefish, no future planning was observed in the cuttlefish tested. They all choose the shelter, whatever this attractiveness, even if this attractiveness was a very low value. One explanation could be that they are very attracted by the shelter. When they are in an open space, they try to avoid direct vision to the experimental open areas. They avoid that. And maybe there is a low drive for food. The question is to make them reach satiety. We give them a lot of shrimps. So maybe at night they were not hungry anymore. So it was not a problem for them just to choose another time a shelter because they will get food just the day after. That was a possibility. And if it's the case, we can wonder whether we could test individuals that are not the same age, and the old cuttlefish are very interesting here because at the end of their life they are eating a lot of food, the females especially, because before laying and spawning the eggs they are eating a lot of crabs, a lot of shrimps. So maybe the drive for food will be much higher, and maybe we will observe some future planning. And I can say you yes, So what we saw is that we have at least shown by now future depending foraging behavior in cuttlefish, not yet future planning behavior. So either because they do not possess this ability, or maybe the paradigm used was not enough to make cuttlefish prioritize a future need rather than present need. Let's finish with the octopuses. So the question was, does episodic memory evolve especially in cuttlefish because they have very specific constraints and ecological demands? And we wanted to do this exactly the same experiment that has been done in cuttlefish. So, but this time not with visual cues, but with opaque pods. The octopus was not able to see what was inside. So one pot with the preferred prey for the octopus is the crab for the octopus, not like the cuttlefish. And the non-preferred prey, the shrimp. And after 1 hour, we were expecting them to go to the non-preferred prey. And after 3 hours, we were expecting them to go back to the preferred prey because the time interval was enough to let the prey replenish. We have done that. We have done that during around 100 trials, and there is no improvement. Octopus do not seem able to learn this replenishing rate, but they are on their own logical. Some octopus are always choosing the pot associated to the non-preferred prey, so very low risk-taking behavior. And some octopus are always going to the pot with the preferred prey, even if it's working 1 out of 2. Very high level of risk-taking behavior. And some other individuals are just alternating. One day this, and one day this, and one day this, and one day this. Each own individual had his own strategy, very logical strategy, all different between them, and all have a behavior very different to what I was expecting. But maybe my question was not well designed, because we have several ways to encode time, and another way to encode time can be sequence order. I can order the events one after the other, and for that I don't need to know the time elapsed. So before starting to design a new episodic memory task in octopus, we wanted first to try if they're able to learn sequence order. So here we had a pool of 15 images, and for a trial we're taking 4 images among this pool of images, and we were showing them the images, 1 minute each images, and a trial presentation 1 minute with 4 images. And so after that we asked them to choose between the 2 among these 4 images, and the correct choice was to choose the picture that was encountered before the other one. So when there's this, they are supposed to choose this image, but if we ask them to choose between these two images, they are supposed to choose this one because it happened in third position and the one in fourth position. And octopus is very good at that. Very, very good at learning sequence order. So maybe they have a way to encode time that is completely different than the way cuttlefish are encoding time. And maybe this time encoding is species dependent. Just to finish, what about future planning in octopus? So this is experiments, is just an experiment making correlate that we've done in octopuses. What happened here is very simple. We have a huge tank. They are closed in 3 parts. Sometimes octopus are in this part, the shelter compartment. They can hide. They have a lot of piece of plastics and shells to hide, but no food. Or they can be placed in this part of the tank where they have a lot of food, but no place to hide. So they are placed randomly in this or this. And after several days of experiencing both compartments, everything was open. They were placed in a central zone. And with this central zone, they had shelters, movable shelters, and they have a prey that can be moved, for example, mussels. And what we were expected is that maybe octopuses would be able to place the food where they know that they have access to a shelter but no food. And here to bring shelters where they know that they have access to food but no shelter. So that was the idea, exciting idea, but no. They are eating the food and they are hiding with everything in the middle, and that's it. So there are some improvement that have been thinking about this procedure, and we hope that the next experiment that are actually running will make things different. But in this case, we're not able to show this future planning ability in octopus. So, do they possess episodic memory abilities? I don't know. At least they are not very accurate to determine whether it was an elapsed time of 1 hour or 3 hours, but we show that maybe they encode time a different way, but maybe they start now to design a procedure testing specifically episodic memory, but this way of encoding time. So we'll do that in the future. And do they plan for the future? By now, I don't know. I hope so, but I don't know. So what we can say to conclude is that some behavioral features are shared with vertebrates, and some features seems to differ among cephalopods. For example, time encoding was the thing that was going out from the experiments, because maybe octopus are using temporal sequence rather than time elapsed. And we've started to try temporal sequence in cuttlefish, and it's much more difficult than octopuses. So it seems that they are both have their preferred way to encode time. So if we try to identify differences and similarities of behavior, the features of these episodic cognition abilities, and the brain structures between vertebrates and cephalopods, and within cephalopods, it will be very important because we will be able to have some idea or insight on the neural prerequisites mediating these abilities. What is the minimal architecture allowing the species to display this complex behavior? And it will be also important, and that's why I like the idea of comparing species. It's important to facilitate the understanding of what are the ecological pressures that may have led to the emergence of these complex abilities. I'd like to thank you.
Well, thank you very much, Christelle, for a wonderful talk. I'll just pause very briefly. If anybody needs to go, feel free to leave now, and then we're going to take questions. So you want to ask a question and then go. Less of the other people. Thank you so much. All right, Matt, you can get the first question.
Thank you for your talk, it was brilliant. I was particularly interested in the future planning in octopus at the end. There's quite a famous, famously documented species of octopus that carries around coconut shells and other objects, and some people take that as indication of future planning abilities, sort of. But that contradicts obviously what you've said with your unpublished data. How would you explain the sort of carrying around of an accessory to?
What you can see when you see octopuses carrying coconuts is that as soon as the predator arrives, they go eat it inside. So it's difficult to distinguish if its behavior is just answering a current question and a current need to protect themselves from a future need to protect themselves. And that's why it's complicated, just to make the difference between two. I don't know that, I don't say that octopuses are not able to plan for the future. Probably they are able to do that, but it depends on a lot of things. Each time, it's like for the cuttlefish experiment, we are making to balance between waiting for the future and the current need. The fact that they are saying the current need, it doesn't necessarily mean that they don't plan for the future, but they prefer answer to what they need now. So it depends on the way you ask the question. Now, much as they have no evidence of future planning, so maybe they have. But the coconut octopus is not necessarily. You can have very lower level explanation for this behavior that can answer a present need.
Thank you. I'm sorry I have to go, but thank you very much.
Thank you, Matt. Yes, at the back.
Can you hear me?
Yes.
Great. Thank you for this very interesting talk. It's my first time listening to research being done on cognition in cephalopods. I'm very curious about the experiment you did with octopus, measuring how they encode temporal sequence. I was wondering, how did you actually measure their recall when you present them the pictures? Like, how do you actually gauge that recall output?
Oh, they choose the picture. When we have the presentation of picture, it's made out of it's not reachable. But when we ask them to make a choice, we present the two pictures and they're able to touch and take the picture they want. So we know if it's a good trial or not. If they take the good picture, they have some food. If they take the bad picture, we take the picture and we come back later.
And what do you think is the underlying mechanism by which you think they are able to encode this temporal sequence? Is it simply because they show this behavior, or do you think why would an octopus do that? What would be the need for that?
Yeah, and I will start to discuss first why I think elapsed time is not a good idea. I will go that first, and after I will go to the sequence. For cuttlefish, they are eating live prey, and of course there are some pods that you know that are very nice prey. A lot of shrimps, for example. We go fishing for our own cuttlefish, so I know we're going to the place, we're going to fish. So okay, there's a nice place to eat some shrimps. If I take the shrimps and I say okay, it's finished, I'll go later. But I know it's a very nice place to retrieve the shrimps. And for the cuttlefish, it's depending on that, because when they catch shrimps somewhere, after a while, they come back to reorganize themselves and to have an optimized partition on the sand. So it's very useful, for example, for a cuttlefish to understand if time is enough to make the cuttlefish, the shrimps come again to the same place. So that makes sense. For an octopus, elapsed time is not as important, at least for foraging, because when you eat a mussel, you're not going to remind that you have eaten a mussel here to come back again, because the time the new mussel will arrive, the octopus will be dead, because it's very long to replenish. That's why for foraging, maybe elapsed time is not very useful for octopuses, but it is for cuttlefish. But maybe encoding the order or events, it makes more sense for the octopus, because they go to one place, there's a predator coming here, when it's coming, I would go there. So maybe that's the way they are using space, and maybe not only depending on foraging, but maybe on which predator, which individuals came at one part. And maybe it's very important for them to know what happened before what, and not necessarily what the time elapsed, but more the order of the events. I think it makes more sense, at least for that, to have different ways to encode time.
Very fascinating. Thank you.
Thank you for the lovely experiments. In the cuttlefish study, where you had the choice of the preferred food or the shelter, I would imagine that shelters are rather important to cuttlefish.
Yes.
And so that's one factor. But also, I understand that when you lock them in the shelter, eventually the door was opened. So what they experienced was a period in the shelter which may not have been very negative, and eventually they got out, and they may remember that they eventually got out. So do you think that might be some explanation for that result?
Yeah, definitely. We lock the arm, but in the arm there's this open part of the arm, and there's the sheltered part, and they're moving. And during the night, we know they swim, so we can see them swimming along the arm because there's no need to hide from the light. So that's very important, and that's why testing adults makes more sense for that, because it will allow the attractiveness of the shelter. Because when they are this side, cuttlefish do not have a lot of predators except marine mammals. When they're this size, cuttlefish can be eaten by fish, by crab, by even big shrimps.
Yes.
So they have a lot and huge amount and diversity of predators. So I think this, the very attractiveness of the shelter and very low drive is maybe much more either equilibrium or reversed when they are older. Because when they are older, they are not trying to find a shelter necessarily when they are 2 years old. Not
It
really.
would depend on their response to humans also, and you probably know quite a lot about their response to humans. Hiding would keep them away from this big dangerous predator, which is the experimenter.
Exactly. The thing is that for experiment that we indeed we have made with adults, I've not presented it here, but with adults, the thing is that they are wild caught, so they are not used to see experimenters. That's why shelters need to have a bit of attractiveness.
Yes.
If not, the experiments is nonsense. So we need to have these needs. They need to be attracted to the shelter, but not that much. And I think wild caught adults have the exact thing. For the 2 years old cuttlefish, really in the lab, shelter, they don't care. They don't care, not going, there's a shelter, they just stay in the middle, just waiting, that is the end of the test. So I think it's maybe the best cohort to test this what is, just to have this perfect balance. Less attractive shelter and higher drive for food.
James.
Thank you, Christelle, that was really fascinating. It's just back to that sort of sequence of events experiment that you did, and I wondered how much of those results could be explained by pairwise comparisons instead of temporal encoding, because you have one object out of the 4 that should never be chosen because it's always going to lose against the others, and you have one that should always be chosen. So could the octopus be just looking at pairwise comparisons and choosing this is always going to be better than that, that's never going to be better than that? We have checked because the images were never the same from 15, but we have checked whether the results were better when we propose a choice between these two, and between these two, and the other one. So we made this analysis, and there is no differences. If it was the case, we would be expecting a lower level of efficiency when they have to show the second image and the third one. It's not the case. It's exactly the same.
I just add to that it's reminiscent of the transitive inference work in psychology, where you do the pairs, and the criticism you raised, James, is exactly what's been done there. And what people did in a rather clever design was to have 2 sets of these stimuli. That would be the equivalent of what Christelle's done. So that you'd say, well, number 1 is always rewarded, number 4 is never rewarded. and you could talk about the relative reinforcement rates of the second one and the third one, right? But if you then have another series with 6, 7, 8, 9 and train them on those, you can then link using 4. Using 5, you can link the 1 to 4 with the 6 to 9, and then you can look at ones that have the same reinforcement rate, and that would then control. I did have a question about the sequences as well. I was wondering, could you also do it with odours? With odours? Because if you could, you can then use that to look at whether they also show source memory, right, of whether they saw it or smelt it. And if they could do that, then you would have perhaps a stronger argument that this sequence is really a feature of the temporal component of episodic light memory.
That's a very good idea. But others with water is a nightmare.
Yeah.
Because everybody will tell you, are you sure that some odor is not remaining in the tank? And you say, okay, I've changed the water of the tank 5 times, and said, well, maybe it was remaining. So that's why.
Yeah, but you've done it with the cuttles. Well, we did it with the cuttles.
Yes, and it's complicated to publish paper with others.
Yeah.
Very complicated, just to be sure that there's nothing remaining. And because if you're not sure that, because for 1 minute you won't be able to change completely the water, so you have to change everything. But someone say, yeah, but you're diluting the others. So the one is more diluted is the one that's how you can control that it's finished, and it's very difficult. Except removing the animal from one time to another is the only way to be sure that the water is completely avoid of these others.
Well, could you do it with tactile things then, with touch? I mean, being a COVID person, I immediately think of sound, but that's not helpful.
Yes, with tactile information, that's what would be perfect. Because the octopus are able to discriminate texture, and they're very good at that. They are very bad at using tactile information or visual information. It's not their main sense they're using. But why we have chosen images is because we wanted to do the same experiment in cuttlefish. Right. It was easier for us to have this thing. And cuttlefish are not touching things. No. They are not neophytic. So if they put an object, they don't like the object, that they won't get close to the object. So it's quite complicated. So just seeing images is easier. That's why. That's not a good argument for that. But but it was the idea of at start. It's using an experiment that we can be done in both species at the same time. But tactile information is very important for octopus. For example, just to make people know how vision is not so important for cuttlefish, you have a locked tank with a huge crab like this. You distract the octopus, you take off the crab, there are small holes like this, and the octopus will check in all the holes. And the crab was this size. That's not the main sense they are using for foraging. They are touching, they are smelling, but there are some visual information are useful, but not prioritized when they are doing things. But they are important to that, so that's why the choice. But yeah, it's a good idea, of course.